Good afternoon, everyone. I'm Sobi Matthew. I'm from ARM. I'm the TF-RMM tech lead. Today, I'll be discussing about the RMM EL0 app framework, which was a feature that we merged in TF-RMM recently, work done by Mate, who is in my team. So basically, I'll be discussing why we are doing it, some reasons behind this work, what capabilities it is giving us in RMM, and some future direction as well. So by now, most of us are familiar with the standard CCA software diagram. So there's the Realm world on left-hand side, and then non-secure. The hypervisor manages the non-secure virtual machines, and RMM manages the Realm virtual machines. I've shown some arrows to show the communication flow between various entities, and previous talks have covered the different standards involved in that interactions. So I just wanted to highlight the features for RMM which are in the pipeline, like device assignment, which includes on-chip, off-chip, coherent, CXL devices, then SMMU stage 1 emulation, planes, large host page size, live firmware activation, live migration. So in short, there's a lot of features that's coming in, and RMM complexity is increasing with more functionality being added, and RMM is a security critical component in the CCA stack. Traditionally, RMM has been a monolithic trusted component operating at EL2. Now, with this work, what we are trying to do is deprivilege parts of RMM to run at EL0 using the ARM virtual host extension. So VHE is an ARM architectural feature designed to make type 2 hypervisors run at the same privilege level as guests. So you have EL2 being able to run applications at EL0. So using this feature, RMM functionality is sandboxed as EL0 application. The application has an isolated address space. Alongside, the build and the binary for the application is isolated with this work, which means that it has a separate linker script. There is possibility to share some object files which is compiled for RMM, but it can be made separate as well. The apps have separate linker script. Yeah, so there's build and binary isolation for the apps, which is very useful, as you will see in the later slides. So this picture shows the design of the EL0 app framework. The dotted lines are the trust boundary of RMM. So even with the apps, all of the apps are within the RMM trust boundary. Like it's not an external user application running at EL0. It's essentially parts of RMM which are deprivileged at EL0. So the trust boundary, the apps are within the trust boundary of RMM. The green lines, so we have a app service layer which exposes some, it's like the host service, the kernel service layer for the application. So we have a RMM service layer which enables the apps to do some privileged operations like reading and writing from non-secure memory, accessing EL3 services, various other services. Every app has a stub, which is customized for the app. So every app will have a glue layer in RMM, which will do something very specific for that app. The Realm virtual machines run alongside as previous. There's no change to that. Now, the app can have several instances. Conceptually, they are like threads in a process, but they are different in the sense that every instance has its own heap in addition to the stack, which is private to the instance. So this instance also has the app-specific register context, the translation context as well. So every instance has, the translation register context, which is private to that instance. Now, the memory for the instance can be either allocated from the per CPU memory within RMM, which is part of the Realm RMM carve-out, or it can come from the auxiliary granular storage from REC or the PDEF. REC is the Realm execution context. So the RMI spec represents vCPUs as a rec. And as part of interacting with RMM, it delegates the rec objects into RMM so that it captures the metadata for the vCPU. And there are some auxiliary granule storage as part of that. And we can make use of that for allocating memory for the app instance. So as I mentioned earlier, this work was primarily done for security, right? Designed to enhance the security of RMM by sandboxing sensitive data and complex functionality from rest of the RMM address space, which is EL2. The sandboxing works both ways. Any software vulnerability in the apps do not affect RMM at EL2. Similarly, any software vulnerability in the RMM at EL2 cannot easily affect the apps, which is at EL0. The other advantage is by moving sensitive data to EL0 app framework, it can help reduce certain CPU vulnerabilities. Like modern CPUs have a lot of performance optimizations, like out-of-order execution, speculative access, data prefetch, which can have side channels, which can lead to timing side channels, which is not good for security. Moving this sensitive data to EL0 app framework means that it's in a separate app address space, which is not mapped always. It's only mapped in to the app-specific address space when the app is getting used. And potentially, in future, if we wanted to harden the leakage of side channels, or we want to mitigate that, we could have some additional, as part of the app entry, we can either flush branch predictors, cache flush, or any other microarchitectural state can be flushed as part of entry into the app. And similarly, when coming back to EL2, the same can be performed. So all of that microarchitectural state can be flushed out, which will help to mitigate against side channels. So this, in that way, it's similar to the address space isolation work that's ongoing for the Linux kernel, which tries to do similar things. The other advantage is, because some of this functionality inside apps are isolated, if the app crashes, it doesn't affect RMM. RMM can continue to do other use cases which are not involved with the app. The crash is isolated to the app. Yeah, so I'll probably, so the apps, as I mentioned, it's packaged as separate L files. This picture shows the overall scheme. So we have two apps being shown over there, and then the RMM core at the bottom. We have a Python script which will extract the relevant sections, and it will append or prepend header and padding. And all of those will get finally packaged into this RMM image. So you have the first app at the top and the second app over there, and then RMM at the bottom. There's a reason why the apps are packaged before the RMM, because RMM has 1:1 virtual address to physical address mapping in its stage 1 MMU. So which is done to make bootstrapping of the MMU easier. Now this means that all the no-load sections of RMM are going to grow towards the higher addresses below. So having the apps before RMM allows RMM no-load sections to grow to higher addresses after it. We don't have to relocate or do any special things over there. Yeah. With respect to virtual address space layout, so the yellow portions, so RMM, when it's running at EL2, it makes use of both the high VA, and VHE introduces two address spaces, as I mentioned before, and it's typically high VA and low VA. The high VA is configured using TTBR1 EL2, and the low VA is configured using TTBR0 EL2. So today, the low VA is used for RMM code data and shared buffers, and the high VA is used for RMM stack slot buffer. And when RMM starts executing the app, the high VA is replaced with the EL0 app's address map over there, and the low VA is disabled while the app is executing. The way this is designed, as I mentioned, high VA is private to each CPU. Every app has a unique ID, which is used as its address space identifier. This helps in optimizing the TLB operations that are needed for switching the translation tables when we switch from EL2 to EL0. Yeah, every app has its own translation table, register, context, stack, heap, and shared buffer. For communicating between EL2 and EL0, there's a shared buffer, and also portions of heap can be used for communication. The heap is mainly used to avoid the overhead in copying data across the shared buffer every time there needs to be a communication between EL2 and EL0. So if there is some frequently used data that we know can be easily shared using a shared address mapping, we put it on the app heap, and only some infrequent data is used passed between the shared buffer. Now, in addition to the benefits I mentioned earlier, the app framework also solves some other issues we had in RMM. So as I mentioned, RMM is building up a lot of functionality, and it makes use of third-party open source live code for that, like embed TLS, TCOS, QCBoard. And for device assignment, we import libspdm. Now, all of them tend to depend on embed TLS in some form or other. And we found that the libspdm depends on the legacy embed TLS API, whereas the attestation side of things depend on the PSA crypto APIs. Now, having a single embed TLS source code exposing two different versions of API, although it works now, maybe in future roadmaps, as Shebu was mentioning in the trusted firmware update, the PSA crypto API is going to be separated into a separate repo, while the embed TLS API might get deprecated. So if some such situations happens, we cannot use a single embed TLS repo to be built within RMM. Now, with the app framework, we are able to isolate the build of each of the app, which means we can use separate embed TLS for each of the apps, as shown here. The red box show the secrets that are currently held in RMM. So as part of the device assignment flow, we have the SPDM key, which is used to set up the secure SPDM channel. There's the IDE key, which is used to program the IDE link between the device and root port. There's a Realm attestation key. So all of this is now moved into the app, and yeah, it's in EL0. The other issue that the other thing that has come up with device assignment is typically when we think about the surface exposed to the non-secure world, we think about the RMM ABI, because that's the primary way the non-secure host interacts with RMM. So that is the attack surface. Now with DA, there's a new attack surface being introduced. That is, because libspdm needs to interact with the device, it directly reads and writes device memory, which is via a non-secure buffer. So effectively, non-secure has a way to feed in data directly into libspdm, not through the traditional RMM ABI. So having the libspdm running at EL0 gives us better protection against any vulnerability in libspdm, which can be used to hijack the rest of RMM. Hopefully, with this framework, any attacks on libspdm will be contained within the box, and it remains at EL0. It affects only the DA use cases. The other benefit is for the device communication, SPDM needs to transition between RMM and non-secure in a yielded manner, as in we need to yield mid-stack. So traditionally, firmwares don't allow reentrancy, as in you cannot stop midway, go back to the caller, and then allow some other call to come through. Reentrancy is not allowed, but with app framework, because it's got its own stack and register context, we are able to do non-secure yield for SPDM communication with this easily. Now, there are some drawbacks. Debugging becomes a bit harder. The first thing to take into consideration is the RMM core is not at the load address of the RMM image. There's an offset, which is, as I mentioned, there are apps being packaged initially, and then RMM core is at an offset. And every app is running in the same high VA address space, which means if you put a breakpoint in the EL0 app, it may match several other apps because all of them are having the same VA. So it makes, debugging the apps a bit harder. One input is to look at the ACID field of TTBR1 EL2, which is giving you the app ID, and that will let you know which app is running at EL0. There is also a performance cost because we have to context switch between EL2 and EL0. So the use cases currently this is enabled is for use cases which is not performance critical, like the attestation flow and the device assignment flow, where the device initially needs to get assigned to the realm. And once the device is accepted into the realm, then everything happens through the data path established between the device and the realm. The sandboxing of the EL0 app increases the memory footprint as well. As I mentioned, embedded is getting built separately for each of the apps. So previously, we used to have one set of object files for embedded. Now, potentially, there are 3 sets because we have 3 apps. So there are 3 sets of embedded being built. Some parts of the app are currently, some parts of our app are mapped in RMM when ideally they need not be mapped. So as I mentioned, we have these aux granules in the rec and pdev. Because this is an initial implementation, we have not optimized this part. So the aux granules are getting mapped into the RMM address space when the rec is running. This need not be the case. We don't need to have the aux granules mapped when the rec is running. So that's an optimization we can do. Also, the BSS for some of the per CPU allocations for the app is coming from RMM BSS, again, which means that this is getting mapped into the RMM EL2 address space. We will be rectifying this once RMM is able to allocate memory from Realm carve-out in a more dynamic fashion. I just wanted to show the log that will appear once the app framework is enabled. So this is useful. This address, this shows the address where the real RMM core is running, the EL2 firmware is running. Then, as part of parsing the header, it prints out a lot of information. So the first app is at this address shown over there. It shows the app name. Then there is the app ID. And then there is various other information, like what is the size of the text, arrow, BSS for that app. And similarly for the second app. So if you want to look into more details about how the app is running and what are the details about it, you can enable the app firmware, app framework logging, and you'll get this information. Just one slide on the fake host. So RMM has a special mode called fake host, where we can build RMM to run as a regular user space application, mocking all of the EL2 functionality. Now, when EL2 app framework was introduced, some parts of RMM is being compiled as a separate process, which means we need to have inter-process communication between the main RMM app and the EL0 app using pipes, and then each of those instances are spawned as threads. Again, there's some communication happening over there. And also, when you run the binary, you have to specify all the app binaries as the command line argument. Future direction. So one interesting thing about this app framework is effectively you have parts of RMM being built to run at EL0, which means that potentially you could run it at Linux user space EL0 as it is with some scaffolding around it. So we think that we should be able to have unit testing for the app by putting some unit testing framework scaffolding around it and run it as it is. Whatever is compiled for the target, we should be able to run it on the host as well. This will enable fuzz testing and also some performance measurement of the app and help us decide whether we need to enable SIMD and SVE on the apps based on the use case. We also plan to enable more optimizations and security hardening of the app framework. Like there are some architectural features like DIT, data independent timing, and SSBS, which is an architectural extension to prevent side channels. So we could potentially enable it on an app basis, thus increasing security. It's also possible, because we have got capability to yield, we can extend it to preemption as well. So currently RMM does not preempt if an interrupt is pending, but potentially with the app framework, if the EL0 app is running, we can allow an interrupt to preempt the app, come back to RMM, and then transition to host to allow the host to handle the interrupt. Yeah, as I mentioned, the app framework enhances fault handling and crash recovery. Live firmware activation, again, this is interesting. So previously, all of the data, BSS of various third-party libraries was packaged as part of single RMM binary. Now, because with the app framework, they are separate, potentially we can, if it is needed, we can do it on an app basis. Some apps, we would be able to reinitialize most of that data based on cold boot information. But for some apps, we may need to migrate that data. So we can do it on a per app basis in an easier manner. The other potential benefit is we can shift some of the requirement-specific variations in RMM to EL0 applications, thus keeping RMM core generic. So one example is we have two slightly different attestation token signing schemes in RMM today. So if we are able to isolate this difference, it's already isolated, but it is possible to have two different versions of the app doing these two different schemes, but then have the RMM core as generic. There is the link to the detailed design guide, which is part of the documentation. Yeah, it also has a list of additional enhancements which we plan to do. And yeah, and then there's the, if you would like to get in touch, if you have queries on this, I've included the link for the TF-RMM Discord channel, and also you can ask us on GitHub issues. Yeah, thank you. Yeah, if you have any questions, please let me know.
Can the EL0 applications cause to each other?
No. So they can't call directly, but they can go via RMM. So today there is one case for which we need to do this. The pseudo random number generator is a separate app. So every time the attestation app needs a new random number, there's a RMM service exposed for random number, for retrieving the random number. And that service will call the app, the PRNG app, pseudo random number generator. We don't want to increase the number of nesting for the apps, because that will mean that we have dependencies between how the apps are initialized and all of that. So potentially, we would like to keep it minimal as possible and maybe have just one app being dependent on another app, but yeah, that's the situation.
So you mentioned actually each of the app can be like running independently. So if something bad happens with one of them, you can actually like still have the others work.
Yeah.
But how do you cleanly handle the like exit from that
right.
app that got impacted? Yeah.
Right. So potential ways RMM could detect synchronous exceptions on that app, right? And if RMM sees that we take a unexpected synchronous exception on that app, we can disable all of the app functionality for that particular app, and then return error back to the caller. And any further calls to that app can be blocked off. Or we may even be able to reinitialize the app we have to investigate that possibility. That's one idea. We can reinitialize the app for the next invocation. But yeah, we can do such things in RMM. Okay. Thanks, everyone.